Now, before understanding physical AI, let's first understand what common sense is. We humans learn about different things in the world. After birth, we slowly understand this physical world, such as its three dimensions. We develop an understanding that objects exist in a three-dimensional space and follow physical laws, like gravity, inertia, and more. It is because we have a model of the world in our brain, which develops from childhood through our perception of the world, interaction, and observation. We know what the consequences of our actions will be. If someone claims that a car can speed through a curve without any risk, it defies common sense because it contradicts the known physical laws of motion. So, to develop common sense and an understanding of the world for intelligent decision-making, we need a world model in AI. We will further understand this concept, but for now, consider that your task is to reach a destination. You can do it either by driving a car, or you can also take a direct flight to reach the destination. Let's say you decided to go by car. This is not a simple task. It consists of many subtasks. One subtask could be driving on the road, and you see a red light. You can either slow down your car by pressing brakes, or you can move on the same speed. Let's say you decided to slow down your car by pressing the brake. Remember, this process also requires a sequence of actions to perform this task. This requires taking action and moving your muscles. You can see that we made a decisions to reach our destination. For that, we also make sequential decisions to slow down a car. There are a lot of other decisions in the process of reaching destination as well. We want to develop an AI capable of thinking at different levels, like deciding to reach the destination by car, applying brakes to slow down the car, or controlling muscle movements, making decisions at different levels of abstraction, just like humans do in their daily lives. Let's build the brain of autonomous machine intelligence. This concept was proposed by Yann LeCun in his work titled, A Path Towards Autonomous Machine Intelligence. First, we will examine the different components and then discuss each one in detail. The perception module receives sensor signals to estimate the current state of the world. For each task, only a small part of the perceived state is relevant, so the perception module represents the world hierarchically at multiple abstraction levels. The world model module predicts future outcomes of actions without actually executing them. It imagines potential future states. This world model is what we discussed earlier as important thing for understanding the physical world. The actor module interacts with the world by performing actions based on the information from the perception and world model modules. It is responsible for making decisions and executing them to influence the environment. The cost module measures the agent's discomfort as energy, combining intrinsic and predicted future costs. The intrinsic cost module is fixed and reflects basic drives like pain, pleasure, or curiosity. The trainable critic module predicts future discomfort using past experiences. Both modules guide the agent to take actions that minimize long-term energy. The short-term memory module stores information about past, current, and future states and their intrinsic costs. It helps the world model predict future states, fill in missing details, and train the critic module using past data. The configurator module takes inputs from all other modules and adjusts their parameters to perform the task at hand. This entire system works together to carry out various tasks. But why do we need such a system? Or in other words, what is the importance of such systems? We know that a teenager can learn to drive a car with approximately 20 hours of practice. On the other hand, AI is trained on vast amounts of data generated by human experts, combined with reinforcement learning. Yet, AI systems still fall short of humans in terms of reliability. This is because humans and animals have a deep understanding of the physical world and its dynamics. They can predict how objects will behave, reason about cause and effect, and adapt to new situations with ease. Let's first discuss reactive policy. Let's say you get an observation from the world. You encode this information into a lower dimensional latent space that contains all the important information of the current state without any noise. You share this encoded information with a policy network, and it returns an action. Now, this action can be taken in the world to obtain the next state of the world as input. But we can also imagine what will happen after taking action using predictor network. This predictor network takes both the state and action and predicts the future outcome of the action. Because we are not actually taking the action in the world, it is like imagining the consequences of the action without executing them in the real world. This is what we know as the model of the world. You can also see this concept in model-based reinforcement learning. There are some other things known as costs, also known as the energy of the state. These are similar to rewards in reinforcement learning, but you can say that the goal of the agent is to minimize these costs. We will discuss this cost in more detail later. Remember, we are discussing Mode 1, reactive behavior. So, we will not be using the predictor to imagine the future, but we will directly take action in the environment. This is to demonstrate actions you take directly without thinking. Let's move to mode 2, which is about reasoning and planning the action. Again, we have an input from the environment, and we feed this input to an encoder to get a representation of the input X. But this time, we want our agent to think and then take the best action. So, this time, we want our agent to learn. So, for this purpose, we generate a sequence of predictions using actions taken by the policy network, where we predict the next state using the predictor network for a sequence. We also get the energy value at each state to determine how good or bad the action sequence is. As I mentioned before, it is similar to the reward in reinforcement learning. Now consider you have energy of each state represented by a value. Your goal is to minimize the sum of all the energy for all the states. Now, remember that we do not update the parameters of the energy function here to get a lower energy value. We also do not change the predictor module. Because the whole network is differentiable, we directly change the actions of the network to obtain the correct sequence of actions that lead to states with low energy. So, this way, we can reason and plan using the predictor module and then take the right action in the environment. This overall structure helps in reasoning and planning. We will later study how to develop these encoder and predictor modules. Also, what exactly is this energy function? But all this in next part of the video.